Hi everyone, in this video I'm going to be discussing the behaviour of ideal gases. So the ideal gas laws provide a set of equations to relate the pressure, temperature and volume of a gas, and it turns out this provides a great approximation for the behaviour of most real gases, provided that the pressure is not too great so we can neglect the interactions of particles, and that the temperature is suitably high relative to the boiling point. The assumptions that go into the development of or the explanation of the ideal gas laws come under what we call kinetic theory, and I'll discuss this in a different video. But today I'm just going to describe the three gas laws you need to know, and also show how they can be combined into a single equation, which is the ideal gas equation. This is something you've already studied. Now's a great time to pause and write down everything you can remember, and otherwise I'll get started on the whiteboard. So there are three experimental gas laws you need to be aware of when describing ideal gases, and you might have done some experiments at school that allow you to test these laws. The first one is Boyles Law. And this relates the volume of a gas to its pressure at constant temperature. So specifically, PV is a constant for a given temperature. And that means that you can write, for example, P is equal to a constant over V, with that constant depending on the amount of gas you have and the temperature. So I can draw this on a graph of P against V, and it will look like this. Obviously, one thing we should note that as the temperature gets higher, the shape of these graphs will change a bit. This is not a particularly good diagram on my part, but these three curves show the case of the temperature increasing. The second law you need to be aware of is Charles's law. And this relates the temperature to its volume at constant pressure. So V over T is constant. And again, the constant you get will depend on the pressure of the gas. But if we were to draw a graph of now temperature against volume, and note that temperature here is in degrees Celsius, we get a straight line, and this intercept here is at absolute zero. So the first two laws are named after famous scientists, whereas the third is actually just called the pressure law. And this says that at constant volume, P over T is constant. So maybe what I'll do is write for each of these what we're assuming is constant. So Boyle's law relates pressure and volume at constant temperature. Charles's law relates volume and temperature at constant pressure. And the pressure law relates pressure at temperature at constant volume. And again, for the pressure law, we can get a similar graph to the one I drew for Charles's law. So pressure now against temperature. And again, this is in degrees Celsius. And we'll get another straight line that again ends at absolute zero. So the temperature of absolute zero, which is around minus 273 degrees Celsius, is very important from the point of view of thermodynamics. So we think that it's not possible to ever go below absolute zero. It's a complete lower bound in the temperatures we can think of. And at this limiting temperature, you would expect the kinetic energy of all objects to go completely to zero. So we've now discussed the three experimental gas laws obeyed by an ideal gas, relating the volume, the temperature, and the pressure. But it turns out these three laws can actually be combined into a single equation, which is known as the ideal gas equation. So if we combine the three results that we've written out, so PV is constant at constant T, P over T is constant volume, and V over T is constant at constant pressure, then you actually get the result that PV over T must be a constant. And that constant we would expect will depend on the amount of gas you have, so either the total number of particles in your gas or the total number of moles. And if we work in moles of gas to start with, the ideal gas equation can be written as PV is equal to nRT, where N is the number of moles and R is the ideal gas constant, which is given by 8.31 joules per Kelvin per mole, where the Kelvin scale is an alternative temperature scale that's the same as the Celsius scale but offset. So specifically, the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15, which means that absolute zero on the Kelvin scale occurs at zero. So we can also sometimes find that it's easier to work rather than with a certain number of moles with a certain number of molecules in our gas. And in that case, the ideal gas equation can be written as PV is nKT, where Kb is the Boltzmann constant. Right, I can just fit this in the bottom, the Boltzmann constant. And those of you that are familiar with, I guess, converting between different sets of units, you'll be able to see that for this these two equations to be equivalent, you need that nk must be equal to little n times r for a given gas. You can write capital N, so the number of particles, as the number of moles times Avogadro's number, which is around 6.02 times 10 to the 23 inverse moles. Okay, so I hope this has been useful. I hope you've enjoyed either learning about or reminding yourself about the ideal gas equations. Please send in questions or requests for more topics if you have any, and otherwise I hope to see you all soon.